A basic design principle in the Wolfram language is that everything is an expression. Things that typically represent data, for example, like numbers and lists, are expressions. Programs like this do loop and this map input are expressions. And more complicated things like graphics and images are also all represented as expressions. All expressions are either normal expressions or atomic expressions. Normal expressions are expressions like lists and programs and other things that have parts, and atomic expressions, or atoms, are things like numbers and strings and symbols that do not have parts. The parts of a normal expression are other expressions. For example, this list of lists, which represents a 2 by 2 array, is a normal expression with two parts, and each part is another list, and those lists are also normal expressions. Arbitrarily complicated expressions are built up using nested combinations of expressions as parts of other expressions. For example, this graphics expression is a normal expression containing a list, and within that list are other expressions representing the disk and the triangle and the color red. In any expression, the expressions at the innermost level are always atoms. In that input, for example, graphics, disk, red, and triangle are symbols, and symbols are atoms. The same expression will often be displayed in different ways or entered with different notations. The most basic and unambiguous notation for entering or displaying a normal expression uses commas and square brackets. The normal expression f of 10, 11, 12, for example, can be entered by starting with an initial part called the head, followed by an opening square bracket, followed by the remaining parts called the elements of the expression separated by commas, followed by a closing square bracket. There are other notations, however, that are used for entering and displaying expressions. A list with elements 10, 11, 12, for example, can be entered as the symbol list followed by square brackets enclosing the elements, but lists are usually entered and displayed with curly braces around the elements. The notation with curly braces is a special notation for an expression with a head of list. There are hundreds of special notations like this. Some of these notations are common and familiar. Expressions with a head of plus, for example, are usually displayed with a plus sign. Subtraction is typically entered with a minus sign. And multiplication, meaning an expression with a head of times, can be indicated by putting factors next to each other with space between the factors. So the space character is in effect part of a special notation for multiplication. The notation using commas and square brackets without any special notations is called full form notation, and there is a function called full form for displaying things in that way. For example, here is a list entered using curly braces displayed in full form notation using the full form function. And this shows that the full form notation for x plus y plus z is plus of x comma y comma z. Choice of notation is very important for constructing readable programs and is discussed in more detail in other sections. The parts of a normal expression can be picked out using the part function. For example, this picks out the part at position 2 in the normal expression f of abc. The part function can also be entered using double square brackets. The head can be picked out using the head function, or the head is also the part at position 0. The head and the elements in that example are atomic expressions, but the head and the elements can be anything. For example, here is a more complicated normal expression where the head is the symbol f, which is an atomic expression. The first element is g of abc, which is a normal expression, and the second element is also a normal expression. In many normal expressions, the head is a symbol like f or g, but the head can be any expression. In that example, the head of the second element is g of x, which is another normal expression. Parts of normal expressions that occur within other normal expressions can be picked out by giving additional elements in the part function. For example, 1, 2 in this input to the part function picks out the second part of the first element in the expression, and this picks out the element at position 2, 0, which is the head of the normal expression at position 2. The numbers used in the part function to specify a particular part are called index numbers or indices, and the number of indices needed to specify a part is called the level of that part within the expression. For example, since one index is needed to pick out an element of a normal expression, the elements of a normal expression are said to be at level 1, elements within those elements are at level 2, and so on. The parts picked out by those last two inputs, for example, are at level 2, since two indices were needed in the part function to specify those parts. There are many common operations where level specifications are used. For example, this input shows the default behavior of the map function, which is to apply a function at level 1. And this shows map used with an optional third argument, which serves as a level specification. The level specification list2 specifies that the function should be applied at level 2. The elements at level 2 in this example are the elements of the sublists. Expressions that aren't normal expressions are atoms. The three basic atoms in the Wolfram language are symbols, numbers, and strings. Although atoms do not have parts in the same sense that normal expressions have parts, atoms can still behave as if they have parts. Atoms have heads, for example. Symbols have a head of symbol, and strings have a head of string. The head of an atom is also returned as the part at position 0, although this is more of a definition rather than a part that is stored within the atom. Numbers have various heads depending on the type of the number. Integers have a head of integer, for example, and real numbers with decimal points have a head of real. Atoms can also behave in other ways like normal expressions. Rational numbers, for example, display in full form using commas and square brackets as if they are normal expressions with two elements. And complex numbers display as sums with a plus sign between the real and imaginary parts of the number, as if the complex number is a normal expression with a head of plus, but complex numbers are actually atoms with a head of complex. There are also in the Wolfram language a few more specialized atoms like associations and datasets and sparse arrays where the atoms represent more complicated structures that are optimized for particular applications. This input, for example, uses the association function to create an association with 3 elements. Each argument in association is a rule giving a key and a value. The keys in this example are the strings w, x, and y, and there is a value associated with each key. Those keys and values are saved in the internal structure of the association. Associations work a bit like lists, except that elements in an association can be selected using keys. This input, for example, picks out the value associated with the key x. The AtomQ function shows that the association is an atom, but that atom contains a lot of information and in fact behaves in some ways like a normal expression. The length function, for example, gives the number of values in the association, which is what would happen if the association was a normal expression. This input uses the part function to pick out the value associated with the second key in the association, which is also similar to what would happen if the association was a normal expression. And full form of the association uses commas and square brackets, which is the notation used for a normal expression. Another example of a complicated atom is a sparse array. This input uses the sparse array function to construct a sparse array expression. The normal function can be used to convert that sparse array to a list of lists, which is the generic way of representing arrays in the Wolfram language. This shows that array displayed as a matrix. Sparse arrays are useful primarily for working with large arrays in which most of the array elements are 0. Even in this small example, the sparse array expression uses less memory than the equivalent array represented as a list of lists, and for larger arrays, the benefits of sparse arrays in memory and computer time can be quite large. The sparse array expression is an atom. That atom does, however, behave much like a normal expression. This input, for example, uses the part function to pick out an element from the sparse array expression, which works just like picking the same element from the equivalent list of lists. And this shows the eigenvalues function, giving the same result whether the input is a sparse array expression or the equivalent list of lists. In this example, since the atom and the equivalent normal expression behave in the same way, this is a case where the distinction between atoms and normal expressions has no effect on programming and is entirely in the internal technical details of how the expressions are stored and in some corresponding performance differences. One other technical detail that can sometimes be useful to know about is that before they are evaluated, inputs involving functions like sparse array and association and rational are normal expressions. Evaluation of this sparse array input, for example, returns an atom, but if that input is held unevaluated, the expression is not an atom. Similarly, this input to rational returns an atom when it is evaluated, but before it is evaluated, that input is a normal expression. Here is an example involving association. This input shows the part function used to pick out the value associated with the second key in an association, which is how associations work. And this shows that same calculation done with the unevaluated association expression, which returns a different result. In this example, the part function picks out the entire second element of the unevaluated association input, which is the entire rule giving both the key and the value. Behaviors like these are typically an issue only in unusual situations, such as in programs that manipulate unevaluated expressions, or when the small amount of time needed to, for example, construct an association atom is of interest. In the Wolfram documentation, a good place to get more information about expressions is this tech note on expressions.